Welcome to the next video in the Systems Programming video series. In this video, we are continuing in section 13.2. And here we are going to talk about creating and destroying processes. So whenever one process creates a new process, and soon we'll look at some concrete cases of C code that does exactly that. But you just imagine that there may be some program that you have run in some program called a.out, and that may be the parent. Then it is possible, using the fork command, among other things, to create a new process. And when one process creates a new process, we call the newly created process the child of the parent, which was the old process. This creates a kind of process hierarchy. And we can see a diagram here. So suppose that you had some C program and it makes two calls to the fork function, which is just a command in C that creates a new process. And suppose that the process it creates, we call that, just for reference, right? There's nothing official about the names A, B, C, D here, but just for reference, we call them that. So A creates the two processes B and C. It will then be possible to control each of these processes. And so suppose that the process C itself also calls fork, and then that spins up a new process, which we could call D. And this diagram shows the parent-child relationship, right? So A is the parent of both B and C is the child of A, but C is also the parent of D, so on. Anytime that a process forks a new process, the operating system creates a copy, and this is fairly important. The operating system creates a copy of... Now, when the fork command is called, this is important, the operating system creates a copy of the calling, that is to say the parent's process's execution state, which includes a bunch of information about the CPU registers and so on, and it creates a new process control struct. But what I really want to emphasize is that it creates this copy of the calling parent's process's execution state. So what that means is that effectively whatever the parent was doing, unless something changes this, which usually you want to do, but if you don't change anything, then the child is actually going to mimic exactly what the parent does. So this is why if you call on the fork function and then you start doing stuff, it almost seems as though that whatever you say to do after the fork gets done twice, because both the parent and the child are doing the same thing, because the child by default is merely copying what the parent does. Now, you can make these things come apart, and usually you want to make the parent and the child do different things. There's rarely a situation where you wish that two different processes were doing exactly the same thing. And so it is possible to get them to do different things, which I'm sure we're about to see, at least very shortly. But one thing that's worth noting before we move on to that, so let's look at this code. So we declare this thing that has type and process ID type, so PID is the variable. We store into it the return of fork, and then we call print with that process ID. Now, what is it going to print? Well, the parent is going to run that code, and therefore it is going to print its own process ID. If that process ID were 12, which it probably will not be, but if the process ID were 12, then it would print 12. But also because the child is likewise running the same code, right? So at this point where the fork has already happened, the child is going to copy the state of the parent, which means that it's going to copy the execution commands that comes after the parent's execution commands. So it's also going to run this print command. Now, for the child, what is that going to mean? Because the child is a different process, and there will be different things. It's not precisely the same thing. It's a copy, right? It's somewhere else in memory, and there are some differences in what it has in memory. In particular, one thing that is going to be glaringly different between the two is that for the parent, the return of fork is going to be the ID of the child. So for the parent, when it prints the process ID, which comes from the return value of the fork, that process ID, which here we're imagining as 14, is going to be the process ID of the child, which again, we're imagining is 14. How is that different from what the child is going to do? The child is also going to print, but importantly, at the return of a call to fork, what you need to know is that for the child, the return value is 0, always. So whenever you call on fork for the child process, that return value is always 0. And so that's why if you run this program, what you should see printed is some process ID. It's going to be some number. Here you would think it's 14, but depending on exactly what's going on your computer, it'll be a different process ID for the child. You'll see this line print some number, which corresponds to the process ID of the child. But you will see the child print the process ID 0, because for the child, this return value is always 0. Now, if you want and this is completely typical, you want the child and the parent to do different things, then you can exploit exactly this feature to say that if the process ID is 0, then you say what the child does, right? Because both the parent and the child are going to run this if command, but only the child is going to have that the process ID is 0. So this causes the child to do one thing, while the parent here, if the process ID is anything other than 0 or -1, -1 is a signal that something went wrong. But anyway, so this is what's going to execute for the parent. Now you can see an example here where we print A. Now that is, let's just think through what's going to happen, in what order. Print A. Well, there's no process other than this process. This, I guess we could call it the main process if we want to for now. And that's going to print A because it's basically the only process in sight at the moment. Now, after that happens, we fork, and at this moment, the parent says that the process ID is some number, which is whatever the process ID that the operating system assigns to the child process. It's going to be different on different machines. But for the child, this value, this PID, is going to hold 0. And at this moment in the code, both the parent and the child are running the same code, but with different values for this PID variable. If the process ID is -1, then we halt everything and say something went wrong. But if the ID is 0, then we say, what does the child do in this example? Well, we get the current ID, and then we print that. Now here, PID should be 0, because after all, that's just the return value of the fork call. But my PID, because we are explicitly asking for the current process's ID, then here, this is going to be whatever the current process's ID is, and it may be interesting on your own machine to run that and see what it says. But so this will be 0, and this will be just about anything other than any positive number other than 0. In any case, moving on, otherwise we do what the parent function says. It has its own process ID, so whatever this is should be not 0, and also not whatever that is. So these are not equal. But this process ID, PID here, is for the parent, because that's what's running here again, right? For the parent, PID holds the process ID of the child that it spun up, right? It holds the process ID for the return of this fork. So whatever this is should be exactly the same as whatever this is. Those should be the same process ID. And then my PID would be whatever the parent's process ID is, which again is hard to predict on different machines. Now, it is interesting to ask, what actually prints, right? What runs first and what runs second and so on? Does the parent go first or does the child go first? Again, this is dependent on your own computer, so that it's very hard to predict if one doesn't know all the details of your particular CPU. So it is possible, and actually the number of varieties here are interesting, right? You might think the parent runs first. Let's imagine what happens if that's what you think, that the parent runs first. Well, what's going to happen? Well, the parent is going to go ahead and say, is my process ID 0? No, it is not. So I'm going to go into the else block. I'm going to print everything here, and then the parent continues. That the parent is then going to print B:, and then my process ID. And so there the parent went first, and then the child goes next. So now, after all that's done, the child gets to go and says, is my process ID 0? Yes, it is. So I want to go into this block of code. I get my process ID, I print. The child also comes down to this line and also prints B:, and my process ID. So that's one way that things could go. That's where the parent goes first. And that would be like this right here, this option 3 of all the options that it enumerates. This is what we just described, where the parent goes first, it out its own print line that is special only to it, and then it prints out this thing that both the parent and the child share. So that's that scenario, and then the child goes second. So what we just talked through is this option 3. If you did the child first, then you'd basically just swap it around. So you'd think that maybe that would be this, right? Child gets to go first, child does everything the child does, then after that does everything the parent does. But the other options are possible. So it is possible for the parent to run a little bit of its code and then let the child run a little bit of its code. And this has to do with CPU scheduling, right? This is, again, just having to do with how your CPU on your particular computer is designed and schedules these tasks. So there's no way to predict this. It's important to know that when you do this forking, the sequence of operations is CPU dependent. And so you may let the parent go first, parent, child, right? And you may do all of the child, or right, which one is which? That's what this would be. So the parent gets to go next for a little while, the child gets to completely run, and then the parent finishes, and so on, right? All of these variations are possible, is the point here. So you just need to know that when you fork, the sequence in which things happen can be determined by your CPU. And so that makes it very hard to predict if you don't do something to control the sequencing, which I feel sure we will learn about in future subsections here. Now, so far though, this is, okay, we have been able to get the parent to do something different from what the child does, but they are both in a sense still running the same program. We are simply using if and else structure to distinguish the process ID so that, in a sense, they both run the same code. It's just that each one having its own process ID runs kind of different parts of the same code. Now, what if you didn't want to do that, right? What if you wanted some child process to run some other program that you've already written, which to work correctly? I think a pretty obviously desirable thing, and that's what execute VP. So I don't know what the V is there. P is almost certainly for process, but execute this, virtual process, maybe something like that. Anyway, and so that's what this does. If you have some program, let's say that here you have the program a.out, and you're not going to give it any command line arguments, then the way that you get your child process, right? So here we're going to fork. The parent is going to do whatever it's supposed to do. I guess you could imagine that down here, there would be other things that the parent is doing. But here you get to tell the child to run a.out. And so here's how that works. You call on execute VP this a.out with whatever command line arguments it's supposed to receive, and this runs a.out. Now, this is a little bit funny, right? We get the return value, which you could pretty well expect. The return value is just whatever the return value of the main function is. But then we say that if the return value is anything less than 0, then error, the call to execute returned. And that's an error. Why is that an error? It is important to know that when you execute, right, when you call this function, it really replaces the program instructions for the process. And therefore, this code should never run. If something calls on this, all that now runs is a.out. Basically, the entire CPU instructions get replaced by the instructions of a.out, which means that this should never happen because it all got replaced by the call to execute VP. And so if you ever reach this line, right, if it is possible to continue doing anything, then that must have meant that some error happened and that this code, this call to execute VP, was unsuccessful. So no matter how you get down here, it should be the result of some kind of an error. And so I think here you see a completely equivalent way of writing the same thing, right? Here, we don't even check that the return value is anything. We don't check the return value at all. We just know, right? This is equivalent code because we just know that if anything runs after the call to execute VP, then that must be an indication of an error. And so that's why we write something like this, because you could only reach this line of code if something went wrong.